Hello and welcome to today's webcast brought to you by LEDs Magazine. I'm Editor-in-Chief Maury Rice. My pleasure to host today's event, Advanced Thermal Management Solutions for LEDs, Design Considerations and Product Applications. Today our presenters will be Pete Ritt, Vice President of Technical Services, and Dr. Richard Bonner, Manager of Custom Products at Advanced Cooling Technologies. We'll get started in just a couple of minutes. First, just a few logistics announcements I'd like to make. I'd like to thank our sponsor, Advanced Cooling Technologies, or ACT, for making today's presentation possible. For those of you in the audience, I'd remind you that it is a live and interactive presentation. You can ask a question at any time. Simply type the question in the Ask a Question area and submit it. We will ask you a couple of polling questions during the presentation. They're just simple questions, multiple choice answers, and we'd really appreciate it if you would answer those questions, and it'll greatly help us evaluate both what you do and help us to present the best webcast we can. If you're running pop-up blocking software, we'd advise you to disable it to view the webcast in the best possible manner, and it's really best if you close down other applications for the best performance. We do support the webcast on many platforms these days. We've always done it via internet on a PC browser. Pinwell now offers viewing on Apple tablets and iPhones running iOS 4.2 or later. You'll have access both to these live events and the on-demand archives. And so if you are using one of those platforms, you should be able to access the material. We will be archiving this event within 24 hours of the live presentation. We'll send a reminder email to all registrants with a direct link. You can also always get to our webcast on the homepage, ledsmagazine.com, under the Resources tab on the far right, or either just ledsmagazine.com/webcast. Now, a bit about our speakers. Pete Ritt's going to provide the bulk of the presentation today. He works in the ACT Technical Services business that provides thermal consulting and design and analysis. He's been granted over 20 patents and holds degrees in chemical engineering from the University of Notre Dame and an MBA from Shippensburg University. And then for the Q&A section, Dr. Richard Bonner is going to join us. He's been with ACT for over 8 years and works in custom products. And he has experience in many advanced thermal topics, including two-phase heat transfer, nanoscale coatings, thermal storage, junction-level cooling, and jet impingement. He holds BS, MS, and PhDs in chemical engineering from Lehigh University. So, Pete, the floor is yours. Welcome.
Thank you, Maury. I'm Pete Ritt, along with Dr. Richard Bonner. We're delighted to be with you. For today's webinar, we'd like to talk about some advanced passive thermal management technologies, heat pipes and vapor chambers, that are being used more frequently by LED device designers to solve challenging thermal problems. We'll explain some of the fundamentals of how these passive technologies work, and then offer some suggestions as to when they should be considered for implementation. Specifically, we'll investigate 3 types of passive technologies: heat pipes, conduction plates with heat pipes embedded in them, which we call high K plates, and finally vapor chambers. We will then discuss 5 LED product examples and how they benefit from these passive technologies. We'll conclude with a quick wrap-up and answer some questions that you might have. LEDs, as we all know, are experiencing increasing acceptance and growth across many market segments. Part of this growth is due to new, higher power LEDs that can be packaged in increasingly small areas. These new, brighter, more powerful products meet challenging customer requirements and satisfy evolving consumer preferences. However, increased power places greater importance on thermal management because of the negative effect that heat has on LED performance. For typical LED devices, 70 to 80% of the input electrical power becomes waste heat. The waste heat, if not properly managed, can have a significant impact on LED device performance. Increasing device temperature is directly correlated to device life. A rule of thumb is that for every 10 degrees C increase in operating temperature over the max operating condition, device life can decrease by 50%. Additionally, many products are wavelength specific. Increasing temperature can cause the wavelength output to shift, reducing the efficacy of these devices. So it is clear that LEDs require thermal management solutions, and as input power increase and package size decreases, these thermal management solutions will be of greater importance to device performance and life. Fortunately for LEDs, there is a precedent that can be taken from the CPU product evolution. Those products, which are also heat sensitive, initially used aluminum extrusion as the preferred thermal management solution, much like they are today for LEDs. But as the processors became more powerful and the laptops and other products became more compact, more advanced solutions were needed. Today, all laptops have heat pipes as part of the thermal solution. We see a similar trend developing with LEDs. However, LEDs have some unique thermal challenges. For example, any thermal management solution cannot encroach on the optical pathway. This means that the path for the heat to be removed from the device must be in the same direction as the electrical pathway. There are often narrow, constricted passageways which cause unwanted heat to build up. The advanced passive thermal management technologies, which we will be discussing today, can quite effectively address the thermal management challenges presented by LEDs. Let's take a look at them. Today, we will be discussing passive two-phase heat transport technologies. We will be discussing heat pipes, heat pipe embedded conduction plates, and vapor chambers. By passive, we mean the devices do not require any external power to operate. By two-phase, we are referring to simultaneously having the working fluid be in two-phase, liquid and vapor, inside the device. Inherent advantages of these devices are they take benefit of the power transport capability of the latent heat of vaporization. They require no input power to operate. They provide years of reliable operation, and they operate with virtually no noise. We will now examine these technologies in a little more detail. First, we'll look at heat pipes. Heat pipes are sealed vacuum devices. They are housed in a metal tube. Inside the tube is a wick structure and a small amount of a working fluid. Most applications are copper tube, copper wick, and water as the working fluid. But there are several other envelope materials, wick structures, and working fluid combinations. Heat pipes are passive, two-phase heat transfer devices that operate in a closed system. To work, a heat pipe must be connected to a hot end, or evaporator, and a cold end, or condenser, as can be seen in the schematic on the left. The difference in temperature between the hot evaporator end and the cold condenser end is the driving force. The heat from the evaporator causes the working fluid to vaporize. Pressure from the vapor pushes it to flow to the cooler end, where it condenses to a liquid. The condensed liquid then returns to the evaporator by capillary force of the wick structure. In the schematic on the right, you can see a cutaway showing the heat pipe structure, including the envelope material, the wick structure, and center vapor path. Fluid inventory control is an important design and processing parameter. Typically, only a small amount of liquid is used in heat pipes. So now that we know a little bit about heat pipe operation, let's look at how this can be put to use. First of all, with different combinations of envelope materials, wick structures, and working fluids, heat pipes can be used over a wide temperature range, from cryogenic to liquid metal, from -150 to 1500 degrees C. Because they are sealed vacuum devices, some working fluids can operate well beyond their nominal boiling point. Water, for example, can be an effective working fluid from 20 to 250 degrees C. By controlling the amount of working fluid and selecting the appropriate wick structure, heat pipes can restart operation after freezing. They are freeze-thaw tolerant. Also, with the right wick structure, heat pipes can operate against gravity. That is, heat pipes can transfer heat downward. Typically, heat pipes can transfer heat around 8 inches against gravity, although gravity-aided operation is generally preferred. In terms of advantages, since boiling and condensing are occurring at the same time, heat pipes can have an effective conductivity of 10,000 to 20,000 watts per meter Kelvin. We can contrast that with copper, an often used conductor, which has a conductivity of around 400 watts per meter K. Other advantages include continuous passive operation, excellent isothermality characteristics, and quiet operation. In terms of heat flux capabilities, heat pipes can operate with heat fluxes up to 50 to 75 watts, with custom heat wicks up to 500 watts per centimeter squared. So when should one consider using heat pipes? Heat pipes offer performance benefits in two main areas, heat transport and isothermalization, with heat transport including heat spreading. Heat pipes should be considered anytime high conduction gradients are a major portion of the thermal resistance. Removing waste heat that builds up on electronics components is the classical application for heat pipes and can be directly applied to LED devices as well. In terms of benefits, heat pipes can be used to reduce the thermal management system size by providing more efficient heat transfer. They can also reduce system weight. Heat pipes are evacuated metal tubes which are lighter than similar sized metal rods. They can reduce required power. Heat pipes themselves require no power to operate and can decrease system hotspots without need for a pump. And in terms of flexibility, heat pipes can be formed to fit countless geometries. The typical bending radius for a heat pipe is 3 times the outside diameter, and they can be flattened to 2/3 the outside diameter. An operating heat pipe bent around a penny can be seen in the upper right. We'll see later on how some of these benefits are realized in LED devices. As mentioned, one of the key benefits of heat pipes is heat transport. Heat pipes can be used to transport heat to external sinks. They can be used, for example, to move heat away from PCBs, chips, and other hot components to heat sinks, which can then be dissipated by either natural convection or with airflow from fans. Heat pipes are capable of transferring heat over long distances with minimal temperature difference, delta T, within the device. The typical delta T is about 2 to 5 degrees C over the length of the pipe. We mentioned typical heat pipes can transfer heat 8 inches against gravity. Gravity-aided and other specialized heat pipes, such as loop heat pipes, can transfer heat over longer distances. Bending and flattening enables increased geometric flexibility to designs. You can see in the picture on the upper right a heat pipe which is bent in 3 dimensions to transport heat away from an electronic component to an external heat sink. The picture below that shows a curved heat pipe removing heat from the center of an electrical assembly to a cold rail. Additionally, heat pipes can be used to move heat away from the inside of an enclosure to the exterior without subjecting the components to the outside environment. This solution can be implemented to dissipate heat from LEDs in sealed packages. The other major transport benefit of heat pipes is heat spreading. One specific embodiment of that feature is the high K plate. High K plates are aluminum conduction plates with heat pipes embedded in them. Aluminum has thermal conductivity of 200 watts per meter K. Typical thermal conductivity for aluminum high K plates is 500 to 1200 watts per meter K, depending on the number, diameter, and location of the heat pipes. High K plates, termed that because of their high thermal conductivity, can be used to reduce hotspot temperatures by moving or spreading heat to less critical areas. They can serve as enhanced conduction-cooled cold plates. They are fully compatible with either liquid or air-cooled chassis. They can be used to improve fin efficiency and lower fin weight. Pictured on the lower right is an application where all of the high-powered electrical components were located on one side of the heat sink. Heat pipes were embedded into the plate to move and spread the heat to the other side of the heatsink and get improved fin efficiency. Plate thickness is typically 4 millimeters, but can be thinner. We have made plates as thin as 1.8 millimeters. The structural strength and weight of the high K plate is the same as aluminum. Aluminum silicon carbide can be used instead of aluminum for direct die attachment applications. A sample AlSiC high K plate is pictured on the upper right. And for reduced weight applications, magnesium can be used in place of aluminum. Shown here is a thermal analysis of an aluminum plate containing several high-powered electrical components, with and without embedded heat pipes. Pictured on the far left is a solid aluminum plate without any heat pipes. You can clearly see the 3 hot spots, 2 at the top and 1 at the bottom. Pictured in the middle is that same aluminum plate, but now with heat pipes embedded in them. You can now see that the max temperature has dropped about 20 degrees C, and the temperature uniformity has improved greatly. Pictured on the right is the actual plate with the heat pipes embedded in it. The heat pipes can be seen as silver lines. This technology has many heat transport and heat spreading applications and certainly could be considered for improving thermal management for LED arrays. Next, we'll talk about vapor chambers. Vapor chambers work similarly to heat pipes, but, due to its shape, can move heat in 2 dimensions. As can be seen in the schematic on the right, in vapor chamber operation, high heat flux input causes the working fluid to vaporize. The vapor then spreads in 2 dimensions. There is wick material all around the inside of the structure of the chamber. When the vapor reaches the other low flux side, it condenses and returns to the high heat flux area via the wick structure. One of the benefits of vapor chambers is that the vapor heat transport yields nearly perfect isothermal heat spreading, as is illustrated on the low flux side in the right side of the schematic. Here, the temperature across that side of the vapor chamber is highly uniform. So in a sense, a vapor chamber is a heat flux transformer. Vapor chambers are often used in conjunction with heat sinks, taking advantage of their nearly isothermal output and making the heat sink more efficient. Typical components of a vapor chamber heat sink assembly are seen in the lower left. They consist of the vapor chamber wick structure in the middle, a copper envelope seen below, and a heat sink seen at the top. Vapor chambers are used to dissipate highly concentrated heat flux regions. They can handle higher input heat fluxes than a typical heat pipe, and they can dissipate that heat more uniformly. As we'll see, it is a great solution for high-powered, wavelength-sensitive LED devices.
This is Maury Wright rejoining now. We are going to take the first of our polling questions. If you could just briefly answer the simple question that should be popping up on your screen, and we'll get right back to our presentation in just a moment here. Richard, I'll turn it back over to you. Pete, I'll turn it back over to you.
Thank you, Maury. Now that we've learned a little bit about heat pipes, high K plates, and vapor chambers, it could be useful to examine exactly how these technologies could be used as part of a thermal management solution for LEDs. In the following, we'll look at 5 different LED applications where they can be beneficially implemented. The first is the remote sink. In many lighting applications, the LED device must fit in a fixed space to accommodate a variety of customer requirements which usually exclude thermal management considerations. A common example is a luminaire design where the ceiling or wall fixture are based on pre-existing designs using non-LED technologies. These designs commonly have both restricted space for heat dissipation through conduction and limited airflow to remove heat via convection. In cases where there is space to remotely dissipate the heat, heat pipes can be used to transport the heat from the device to a heat sink located elsewhere. This is called the remote sink. The remote sink solution has a heat pipe in direct contact with the LED device, a PCB or similar component at one end, which serves as the evaporator. At the other end, the heat pipe is connected to the heat sink, the condenser. A sketch of a conceptual design can be seen on the lower left. Here, two heat pipes are in direct contact with both the heat generating component at the bottom and the heat dissipating fins at the top. A wall or other enclosure can be placed in between the LED and heat sink to separate the two. In the example on the right, a single heat pipe is used to transfer heat from the source on the bottom to the heat sink above it. A thermal image on the right shows heat being transferred from the hot yellow LED device to the blue, green, yellow heat sink above it. The presence of the green and yellow within the heat sink shows that the heat pipe is effectively transferring heat from the device to the radial heat sink fins. Heat pipes can efficiently transfer heat approximately 8 inches against gravity with minimal thermal gradient, and even greater distances when gravity assisted. Note that the number, size, shape, and location of the heat pipes would be specific to that design. Case number 2, extrusion isothermalization. In some cases, it is not possible or desirable to have a heat sink in a remote location, bay and/or outdoor lighting products, for example. Frequently, large extrusions, typically made of aluminum, are utilized. Heat dissipation occurs through conduction, resulting in large temperature gradients across the heat sink structure, with the highest temperatures found closest to the LED heat-generating source. As we have mentioned, the excess temperature has a negative effect on LED device life and performance. What can be done to mitigate this? We talked earlier about how embedding heat pipes in an aluminum extrusion can be used to more effectively spread heat in that structure. The same benefit can be realized by inserting heat pipes into these large heat sink extrusions. The heat pipes themselves will isothermalize. By doing this, they will spread the heat through the heat sink. This heat spreading reduces the thermal gradient and likewise reduces the max temperature at the LED source. Benefits can be taken in different ways, such as one can run the device at a desired higher temperature and reduce the risk of overheating, or one can reduce the overall size of the heat sink. Our testing and analysis has confirmed that the longer the extrusion, the more benefit from the presence of heat pipes, principally because of the larger available area. As seen in the graph on the upper right, the percentage improvement in thermal resistance with heat pipes increases approximately linear with increasing heat sink length. For example, one can expect to see a 5% improvement in thermal resistance for a 5 centimeter long heat sink. That improvement can be increased to 30% for a 30 centimeter long heat sink. Additionally, one can expect the benefit will be more noticeable in natural convection heat sinks as the fan operation plays a major role in forced convection performance. Let's look at a specific example seen in the upper right. In this case, heat pipes were embedded in a 200 millimeter long radial heat sink that was dissipating 100 watts of heat. As seen in the center of the thermal images at the bottom of the page, addition of the heat pipes decreased the maximum temperature 10 degrees C, which, as mentioned previously, could increase device life by 50%. So we see here an example of using heat pipes to isothermalize a heat sink to get better performance. The third case, heat sink size, weight, and power, again uses embedded heat pipe, or high K plate as we call it, but takes the benefit in a different way. It is well known that placing a discrete heat source on a large metal heat sink will produce large thermal gradients as the heat slowly conducts and dissipates heat to the external fins. We have also discussed in this presentation that embedding heat pipes can increase the thermal conductivity from around 200 watts per meter K to 500 to 1200 watts per meter K offering the opportunity to reduce heat sink plate thickness and fin area. This approach can be implemented in a variety of LED applications, including large arrays, outdoor lighting, as well as some downlighting applications. Let's now look at what kind of benefit we can expect. Here is a heat sink size and weight analysis with and without heat pipes. Total heat dissipation is 150 watts in both cases. The conventional metal heat sink is 12 inches long, weighs 9.6 pounds, and has a base thickness of 0.6 of an inch. Introduction of 5 heat pipes, 3 in close proximity to the heat source and another 2 a little further out for heat spreading, can have a dramatic effect. The overall length can be reduced to 10 inches and the weight can be reduced to 6.3 pounds, an overall material reduction of nearly 35%. Here are some actual thermal images that demonstrate the improvement. The high K heat sink seen on the right more effectively spreads the heat, as can be seen in the yellow area surrounding the source, even though the heat sink is shorter, lighter, and thinner. The improvement is directly attributable to the addition of heat pipes, which can be seen as red lines in the picture on the right. The next example of passive heat transfer technologies for LEDs is directed close to the source of heat. Obviously, it is advantageous to dissipate heat as close to the source as possible. This can be difficult as electrical isolation requirements must be satisfied, otherwise the device will not function. Unfortunately, in many cases, electrical isolation is only achieved using materials that are thermally insulating, such as with FR4 boards. Recently, work at Advanced Cooling Technologies has explored adding heat pipes to the structure of metal core printed circuit boards to help spread the heat right at the source. You can see in the picture on the right an example of heat pipes embedded into an MCPCB. Heat pipes are seen on the left in close proximity to the circuitry. The circuit side is seen in the image to the right of the embedded heat pipes. Let's next take a look at some results. As we have seen, embedding heat pipes can provide much more heat spreading, enabling lower operating temperatures and or smaller heat sinks. Here we see a 3 LED structure on the lower right. A thermal image of that structure is seen on the left. The temperature scale is only 10 degrees C, from 58 to 68 degrees C, to demonstrate the heat spreading capability of this concept. Measurements have shown that the embedded heat pipes can reduce the heat spreading resistance by 45% over standard aluminum MCPCBs and even 15% over copper ones. A valuable improvement, particularly so close to the heat source. Our final example is for a growing number of high-power LED applications, such as UV curing devices. These products typically use high power, requiring dissipation of hundreds of watts, but must maintain tight temperature range so that the output optical wavelength remains constant. The problem is further aggravated because an additional thermal interface layer is needed between the heat source, typically made of some low thermal expansion semiconductor material, and the heat dissipating device, usually copper or aluminum, which have much higher coefficients of thermal expansions, CTEs. Typical interface materials include thermal gap pads and thermal paste. Without such a thermal interface layer, the different materials' coefficient of expansion will result in the heat source device cracking or severing from the heat dissipating device. Unfortunately, the presence of this thermal interface layer increases the overall thermal resistance and likewise increases the temperature on the LED device. The thermal management solution is analogous to some laser diode applications, and fortunately, the solution can be the same as well. Let's look at this in more detail. With both heat pipes and vapor chambers, it is most advantageous to have water as the working fluid for both cost and performance reasons. Copper has been shown to have excellent compatibility with water, but copper has a relatively high CTE and would be thermally mismatched with common high heat load LED devices and would require a thermal interface layer. Additionally, conventional wick structures have limited performance capabilities which may not always satisfy requirements for high heat load devices. The desired solution is to have a water-compatible vapor chamber that is CTE matched to eliminate unnecessary thermal barriers and has a wick structure designed for high heat flux devices. Such a device is available and has been called the CTE matched vapor chamber. This unique device has been demonstrated to dissipate heat fluxes as high as 700 watts per centimeter squared and 2 kilowatts overall. The overall envelope structure is aluminum nitride with direct bond copper exterior. The copper on the inside of the vapor chamber ensures the well-known copper-water performance is maintained. In areas where the heat source is to be attached, the copper layer is removed, exposing the aluminum nitride. Aluminum nitride has a CTE of 5.5 parts per million degrees C, much closer to common semiconductor materials. Devices can be directly attached to the vapor chamber, eliminating the need for a thermal interface layer. Additionally, there is a unique wick structure located at the heat source. It is a combination of very thin and very thick wick material co-located at the evaporator. The thick wick collects the condensate returning from the condenser portion of the vapor chamber and delivers it to the thin wick area. The thin wick quickly evaporates the fluid, achieving very low thermal resistant values. An example of the thin, thick wick structure can be seen at the bottom of the page, termed lateral liquid delivery. This structure has been shown to have a very high critical heat flux, CHF, with an evaporator resistance of only 0.05 degree K centimeter squared per watt. The CTE matched vapor chamber is an excellent solution for high-powered LED devices.
Hi, it's Maury Wright coming back again, and we're going to do our second polling question. And unfortunately, I sent the wrong one the first time, so these actually came out of our order to you in the order they were intended. But you should be able to still answer this one just fine, and we would certainly appreciate your cooperation. Thanks, and we'll return to Pete.
Thanks, Maury. In summary, as LED devices become more accepted and more prevalent, customers are requiring higher performance products in smaller package sizes. This puts an increased burden on thermal management on LED device designers. The conventional metal heatsink solutions will continue to be implemented wherever practicable, but are more frequently be found to be insufficient for a variety of performance and size reasons. Fortunately, there exist passive two-phase heat transfer technologies, heat pipes, high K plates, and vapor chambers that have provided many successful examples of thermal management solutions in the CPU and more broader electronics industry. Those same technologies can be applied to many LED devices as well. We presented today 5 examples of how heat pipes, high K plates, and vapor chambers can be implemented to solve real LED thermal management issues. The remote heatsink demonstrated the heat transport capability of heat pipes. Heat can be effectively moved 8 inches away from the source against gravity, and even more when gravity aided. The extrusion isothermalization showed how heat pipes can reduce the peak temperature, 10 degrees in the example shown, by spreading the heat more efficiently across the heat sink. Extrusion size, weight, and power showed that heat sink size can be decreased 35% in the example shown through implementation of heat pipes without degrading heat sink performance. PCB level spreading offers thermal management solutions very close to the heat source, reducing heat spreading resistance by 45% over aluminum metal core printed circuit boards and 15% over copper ones. And finally, for very high heat flux requirements, such as some LED UV curing applications, the CTE matched vapor chamber offers high heat flux capability over 500 watts per centimeter squared with low evaporator resistances. All of these solutions are based on technologies that have proven track records for long, safe, reliable operation and can be expected to find many new applications with the proliferation of LEDs. We thank you for your attention, and we'll try to answer some questions that you might have.
Thanks, Pete, for a very compelling presentation. For those of you in the audience, we'll get to the questions just here in a second. Just a couple of other notes. You can still ask a question, by the way. Just type it there in the question area and submit it. Several of you asked about a copy of these slides. Unfortunately, we did not get them posted in our resources area prior to the presentation, but I've checked during the presentation, and we will be able to provide those. So when we post the archive of this webcast no later than tomorrow, if you go back and log back in, you'll be able to download a PDF copy of the slides. So with that, Dr. Richard Bonner is going to take some questions for us. And the first one is, are there any software or calculation tools available to predict heat pipe performance?
Thanks, Maury. That's a good question. In my view, heat pipe performance is best split into two categories, what I would call heat pipe limits and calculating the heat pipe thermal resistance. I'll start with the limit analysis. The heat pipe limit analysis refers to the capillary, entrainment, and sonic limits that Pete briefly introduced. These calculations essentially predict the maximum amount of power that can be transported by a heat pipe without going into a dry out stage. These limit calculations can be done actually most readily by lighting designers and engineers simply by using ACT's online calculator. If you go onto our website under the resource sections, you'll find that's pretty easy to use, and a lot of our collaborators find it pretty useful. Now I'm going to go back to the second category of calculations, the thermal resistance calculations I referred to. Thermal resistance refers to the temperature difference or the thermal driving force required to acquire and dissipate heat. To estimate the thermal resistance of a heat pipe, or more importantly, really the thermal resistance of that system-level heat pipe heat sink solution, there are modeling strategies to implement heat pipes into commercial CFD or thermal FEA packages. Usually these strategies rely on assigning effective thermal conductivities to the wick structure and the vapor space of the heat pipe. However, these performance predictions are very sensitive to those effective thermal conductivity values that you assign. Actually, I've seen a lot of mistakes made by lighting designers and engineers when doing this. So I would strongly advise working closely with the heat pipe vendor to help guide you through the process, or even a lot of those heat pipe vendors like ACT will provide thermal analysis services to do those types of calculations.
Very good. The another thing that Pete I know touched on a little bit, but how does the orientation affect heat pipe and vapor chamber performance?
Good question. Yeah, I saw this one from a number of the webinar attendees. Orientation strongly affects the capillary limit of heat pipes. That's the capillary limit being probably the most predominant of those dry out limits I just discussed. When operating against gravity, or in other words, if your heat source is located below the heat sink or the condenser of the heat pipe, the wick structure now has to work harder to actually pull liquid back towards that evaporator so that you can go into that heat pipe recirculation process. If the evaporator is below the heat sink, the heat pipe can operate in reflux mode, meaning that condensing liquid can now just drain and is aided by gravity to return the fluid back to the evaporator. If you want to gain some practical understanding to see what the magnitude quantitatively is, I would urge you probably to go again to our online calculator and run a couple simulations. You'll see the effect can be pretty dramatic. In regards to thermal resistance, the orientation really has negligible effect provided you're operating within those heat pipe limit boundaries. So, thanks, Mark.
So what are the options and considerations in selection of working fluids?
Sure. Really, your primary concern is thermal performance, and that's largely going to be driven by the thermal property or the thermophysical property values of the working fluid. Practically, in our industry, we can quickly choose working fluids by looking at merit number curves. So, a lot of academics have put together these numbers that take ratios of the important physical properties, and we quickly plot them versus temperature to see which fluids look attractive. Of course, building on years and years of practical experience, we sort of know what the answer is usually before we even look at the curve. For most electronics cooling temperatures, especially above the freezing point of water to, like Pete said, 250 C, water turns out to be the best working fluid, as boring as that sounds. However, if you need to operate, really get cooling below the freezing point of water, there are other fluids such as methanol, ammonia, which have pretty good attractive thermophysical properties for heat pipes. If you want to go above the working range of water, maybe if you're in materials processing or some other application, there's also working fluids, as Pete said, that can go up to easily 1100 degrees C with high reliability. Equally, although thermal performance really is the key driver, you also have to make sure that you choose an envelope material or tubing and wick material that's compatible with your working fluid. If the working fluid isn't compatible, it'll break down, generate non-condensable gases that can harm the heat pipe operation. So you really want to make sure you're choosing a material system that's compatible. With water, again, the most economical option is copper. If you're using ammonia, it's actually very incompatible with copper. You want to go towards aluminum. Those are just two common examples. So unless you have a real reason to use a different material, I would recommend choosing it based on thermal performance and then choosing a material that's compatible.
Here's another copper and water type question, and one that Pete, I think, did address briefly, but one that really might come into play in one of these outdoor applications in certain parts of the world where it gets very cold. If copper and water are used in applications, can they be used in applications where freezing is a concern?
Sure, absolutely. Actually, as a matter of fact, our military customers who we provide copper water heat pipes to demand that we cycle our heat pipes between minus 40 C and 85 C and then demonstrate successful operation. So it's definitely doable. Really, the key comes down to how you process your heat pipe to make sure you don't have any excess fluid that could cause bulging of the heat pipe. Usually what we'll see is if your heat pipe or your heat sink is 0 degrees C, we have to remind customers you don't have a cooling problem because you're probably well below your operating temperature in that case. If you do have an application where, say, your LED needs to operate or be cooled below 0 degrees C, then I would recommend going with a different working fluid. But if it's really just about survivability, you shouldn't have any problems using water as the working fluid. Thanks, Maury.
What about wick structures in the materials? Are they different for heat pipes and vapor chambers?
In terms of the material of the wick structure, we're pretty much using the same thing. I think if you do an industry search, you'll see sintered copper powder being a popular wick structure, screen mesh, other types of mesh. So really, we're going to be using the same thing. However, because when you go to a vapor chamber, you do have more flexibility during the manufacturing process. You really have access or better access to that evaporator, whereas with a tubular or cylindrical heat pipe, it's more limiting. But I would say, in general, you're using the same materials, but you do have more flexibility when you go to a vapor chamber. Thank you.
Okay. As I understand, the heat pipe just transfers heat from one place to another, so a secondary heat sink is still required. Is that correct?
That is correct. The heat pipe is really a superconductor of heat that allows you to spread heat or take it from one place to another. But ultimately, you still need to have enough fin area to take that heat and dissipate it to air. So that's why hopefully what was learned from the case studies that Pete showed is that the heat sink or that air-cooled heat sink that you need, that size can be reduced or the performance can be improved by using heat pipes. But you're still going to ultimately need something to dissipate that heat to air.
We got more about temperature extreme. So in outdoor applications where the ambient can rise to minus 40 C, I think the question has got it backwards. But anyway, the question says the cooling is not very cool and the delta T required for the heat pipe is reduced. But can you comment on outdoor use in hot climates? I think it's really the crux of it.
Right, I can comment on outdoor use. To be quite honest, the heat pipe, when you're using water as a working fluid, as you increase temperature above 20 C, going towards 100, even 150 degrees C, the performance of the heat pipe actually improves. However, I have to note that you're still up against the same air cooling limited that I just referred to in the last question. So you're operating at a hotter temperature isn't going to do anything really to change the performance of the heat sink itself. So I'm not sure if that answers the question, but I think in regards to the heat pipe performance, we're not worried about the heat pipe performance degrading as you get hotter. But like I think the author of that question was alluding to, yeah, thermal management does get more challenging as you start losing available delta T, for sure.
We have quite a few questions that all are kind of a different approach to asking about cost of these technologies you discussed today. I know that that's a question that is very, very application specific, but could you perhaps generalize a little bit in maybe the cost of these technologies compared to obviously more than passive heat sinks, but more effective and maybe even to other active cooling techniques?
I'll take that one, Maury. It's really a difficult question to answer because it is application specific, as you mentioned. We talked about in the presentation today that heat pipes are used in laptops where they cost, pennies. There are also many applications for custom solutions where they're one or twos, and they can be, hundreds of dollars on there. So we really have to look at each case individually. Volume is a big driver in deciding what the cost will be, and there's a pretty wide price range for that.
We've got a couple of questions tied to printed circuit boards and the use of these technologies along with printed circuit boards. One says, is there a minimum metal thickness required to incorporate a heat pipe at the metal core printed circuit board level?
Yes, I would say there is a minimum thickness. I believe in our development efforts, 80 thousandths of an inch or about 2 millimeters is really the thinnest we can do practically. Of course, with more development, you can always push that envelope. We would like more than that, something in the 125 to 160 range would be nice to have. Really, it comes down to how far you can flatten your heat pipe, and also it's related to how much power you want to try and dissipate, because when you go to those really small MCPCB board, the really thin ones going to 080, you're going to start with a very small heat pipe to begin with, and I think a phrase we like to use is small heat pipes transfer small amounts of power, so that definitely becomes true at some point.
Okay, very good. Well, I'm afraid we're out of time for questions today, and there are some we didn't get to. We'll maybe consider of some kind of article in the magazine or on the website to address some of the additional questions. On behalf of LEDs Magazine and Pinwheel Corporation, I'd certainly like to thank today's speakers, Pete Ritt and Richard Bonner, and thanks again to ACT for sponsoring today's presentation. I'd remind you that the presentation, Advanced Thermal Management Solution for LEDs, Design Considerations and Product Applications, will be archived by tomorrow sometime at the worst case. You can always get access to that at ledsmagazine.com under the Resources tab, or just ledsmagazine.com webcast. We will be sending all of you registrants an email with a direct link. Our next webcast will take place Thursday, September 26th. It will feature speakers from LEDs Magazine, Mentor Graphics, Allegro Microsystems, and Alpha Alent, and the topic will be LED system design for automotive applications. I truly thank all of you in the audience for taking the time to join us today. I know your time is very valuable, and we appreciate it, and we look forward to bringing you future webcasts. Have a good day.